Hello everyone, 7:30 at our time to start our discussion. So today we had very interesting topic of pipeline architecture. This is lecture 14. I hope you guys had time to review it before coming to the class. Any question on that topic? Anything you want me to discuss? In the meantime, let me just see if there is anything on the discussion side. No, we are in module 6, right? Module number. No, we are in module 7, pipeline architecture, 2 lecture. Okay. Module 7 discussion, nothing. I don't see any. Okay. Then let me just give you the overall concept of this pipeline in terms of the state machine. Remember in the project 2, you have implemented a 5-state machine, instruction fetch, instruction decode, execution, memory, and write back phases. How this pipeline concept fits into that picture, okay, that concept. That's the one I want to explain to you tonight. Let me share my screen with a whiteboard. Okay, so I'm just preparing that. So we have these 5 phases: instruction fetch, instruction decode, execution, memory, and write back. Okay. Now let's quickly recap what it means for so far in the execution of instruction. Let's say we have instructions like these. Let's say these are 4 instructions that we want to execute. And so far what we have implemented in our processor in project 2, how it goes in. It starts with instruction fetch. Let's say it's in the instruction fetch, the state, and it's fetching the first instruction, right? So it's fetching the first instruction into our system, and then what it involves. It involves in that point. It involves basically this resource, right? It involves this resource, the memory. It is fetching the instruction from the memory, and then in the next it goes into the next state. Right? This instruction goes into the next state. Why? Order bring forward. Okay. Next, so as if you can imagine, your instruction is now, is in the instruction decode and execution phase, and resource wise you are basically using this one at that point, right? And then from here your execution processor moves into the exe phase. So instruction, it goes into this state, and your instruction is in this phase. At this point, your resource wise, you are using this, right? And then from here, next clock cycle, it goes into this memory phase. Let's say it has something to do with the memory. So it goes and involve the memory as a resource, and then write back, which involve register file as a resource, and your execution moves from here to there. And then it's basically it's done after that. So this is done. And then this guy moves to fetch the next instruction, right? Instruction 2 is fetched. So your memory is involved there. Instruction 2. So your memory as a resource involves, then instruction 2 goes into this phase. So your register file is used. Instruction 2 goes next into this phase. ALU used. Instruction 2 goes into memory. Maybe this is used. Then it goes into the write back phase. This is used, right? Now you see when we, from the starting of the instruction 2 or any instruction, at each phases, like let's say it is in the IDRF phase, memory as a resource is free to do, right? This is doing nothing. And ALU also free, it is doing nothing. And similarly, when this goes into the EXE phase, your ALU is now active, but register file is free to do any operation, or thus the memory is free to do any operation. So that's the point that pipeline architecture wants to take leverage out of it. So how it does is this way. Let's see. Let me draw four things. Okay. Now, first cycle, when it start fetching the instruction 1. So memory is used. And then when instruction 1 goes into the next phase, your register file is involved. Pipeline architecture take the advantage and fetch the next one. That means at this point, your memory is being used for instruction 2 fetching. Then this guy moves into EXE phase. That means now it is actively using the ALU. This guy moves into the IDRF. Now it is doing actively using the register file, and memory is free. So now this architecture, this processor brings the fetch the instruction 3, which is now using the memory. And now what happens next cycle? Instruction 1 goes here, instruction 2 goes here, instruction 3 goes here. That means ALU, instruction 1 is using the memory now, instruction 2 is using the ALU now, instruction 3 is using the register file now, and it wants to bring in instruction 4. Now here you see in this strategy, now at this time point, specific time point, your memory is being accessed by both the instruction 1 and instruction 4. Now that is the conflict, and that is the structural hazard that we talked about towards the end of this lecture, that how can we solve this problem? Now think, your instruction 1 at this point is doing what? It is probably writing something onto the memory or reading something from the memory, like writing some data into the memory and reading some data from the memory at this point. Whereas the instruction 4, how it is accessing the memory? It is to access the instruction from the memory. And remember, like, we stored the instructions and the data in a separate part of the memory. Remember from your assembly language programming conception, right? Your text part, and there is a data part. Data part goes into the data memory section, and the text part goes into the text memory, or your machine code goes into the text memory section. So we take advantage of that concept and also now split out the memory as a device into 2. we do this thing. Let me redraw the system now. Now it is not a memory. Let's call it a data memory. Okay. And we are walking towards the Harvard architecture. So, and we do separate the, we send it back. Okay. Duplicate. We call it an instruction memory. So there are two different memory we're talking of now. Instruction. Oh, what happened? Okay, let me just do this. Okay. Now, as we separate them out, an instruction memory and data memory, now we don't have a conflict. Instruction 4 at this instruction fetch is using instruction memory, and instruction 1 is using the data memory. That conflict, structural conflict, is gone now. Okay, now how about next phase? Instruction 4, instruction 1 goes into write back. That means it is using this guy. Instruction 2 is in the memory. So that should use this data memory. Instruction 3 is in ALU, exe phase, so it's using ALU as a resource. And instruction 4 now want to use the register. Boom, there is a conflict. How do we solve this problem? Now see, your instruction 1 is specifically writing into the register file, whereas instruction 4 is reading from the register file, right? So there we solve this kind of structural problem. We call it a hazard, data hazard, through allowing this guy to read and write in parallel. So conceptually, that's what is being shown in or drawn in that pipeline timing diagram, saying that, hey, this guy is doing read and other guy is doing write onto that. Maybe this is not a right thing to do here. So remember, like in the timing diagram, we have shown you when something is in the register reading phase, it is shown like this. This is register read. And whenever some action is doing on a write onto the register, this is a register write. This represents that one, like it is using the writing part of it. And how it is possible, like remember we have the address bus, write address bus separate out, write data is separate out. We have read and write signal, so we allow them both to be one, and we have separate these your read address 1 and read address 2 as well, and we have separate output, right, for read data 1 and read data 2. So everything is separate. What we all did, allow little bit change modification in the digital circuit on a register file to allow read and write in parallel at the same time. And that's where we can resolve these conflict. Now, next clock cycle, let's say only there is a fourth thing to do, accomplish. So instruction 1 is done. Instruction 2 moves into a write back. So this will start using the writing part of the register file. Instruction 3 is in the mem, so it uses the data memory. Instruction 4 is in the exe, so it will go and start using the ALU. Then instruction 2 is done. And then instruction 3 moves on to the write back. So it goes into here. Instruction 4 goes into the memory. It goes and access the data memory, and then instruction 3 is done. Instruction 4 goes into the write back. It uses the register file. Voila, done and done. So now you see that it actually takes less amount of clock cycle just by using the resources very wisely. Like, we don't let any resource sit idly. We just keep using them as much as possible, and that is the basic philosophy of the pipelining architecture. Question. Okay, so remember, this pipelining architecture is basically, it is increasing the performance by increasing the throughput. Remember, we have this term throughput we learned in the last lecture. Your individual instruction, if you see, it still needs this 5 cycle. It still needs to go through instruction fetch, decode, exe, mem, and write back. It needs to do that, but while it is accomplishing one phase and another, in parallel, we are putting into the other instruction into the other phases. And that's why it is kind of, it is said this is a pipeline, an assembly pipeline business, kind of that thing, which accomplishes each of the tasks by each of the resources in parallel to each other to keep increasing the throughput of the entire process. And of course, as we have experience in this small example as well, there are gain barrier, like we cannot just infinitely put more stages and get more performance out of an architecture. Mainly actually three type of hazards or problems are there. One is structural, that we just resolve, like separating out the data memory and instruction memory, and also allowing parallel read and write onto the register file. That part we resolve the structural. Then there is the data hazard and the control hazard. That is the part of the next lecture, which tells us data hazard is this, like maybe instruction 2 is depending on the outcome of instruction 1. That means till the instruction 1 is done, your data is not ready to be consumed by instruction 2. What should we do? We need to wait till that instruction 1 is done. So that's one way, and that would decrease the performance very significantly. And we'll see how we actually mitigate that problem. There is some concept called data forwarding. We'll learn about that in the next lecture. And now there is another type of hazard called the control hazard. What it means, this instruction, let's say instruction 1 is in this phase, and then this instruction is kind of a condition test and jump, like BEQ or BNE, that kind of instruction. That means until and unless this instruction, let's say this is BNE, R1, R2 to some L1. So that means depending on the outcome of this comparison, you probably need to pick either instruction 2 or instruction 4. How do we solve it? Like which one to pick up? Because we haven't, at this point, we haven't yet know that what is the comparison outcome would be. We cannot pick up. So one way is to again stall, wait till this comparison result comes in. That means when this instruction goes into the memory phase, the comparison is done in the exe phase, and at that point only we can either, depending on the result, we can bring up instruction 4 or instruction 2. But there are other technique also called it's called a prediction. So it goes and do some prediction, and let's say it predicted to be instruction 2, and go with that. And if it sees that prediction is wrong, then it kind of roll back all the artifacts of that instructions 2 and start from the instruction 4. So we'll learn about that in the next lecture. Yes, someone is trying to ask a question.
Yes. Sorry, I didn't really understand. What is the control hazard? I'm not understanding. Sorry.
So control hazard would be something like BNE. Like let's say your instruction, current instruction is BNE. Okay, R1, R2. It is jumping to some level. That means it is kind of saying that if R1 is not equal to R2, do something else, right? That means at this point, you can possibly invoke, either go into instruction 4, your next instruction can be instruction 2 or instruction 4, depending on which way this comparison goes, right? If it is an else part, it goes there, let's say, and if it is other way, it goes into this part. So at this point, you don't really know what instruction to fetch for this instruction fetch. So that's control hazard. So, Yorick, it is in the next lecture. I'm just bringing up front of this topic. Please go through the next lecture, and then probably this concept will be clear to you.
All right, thank you.
Okay. All right. And then what we mentioned about this one, like we splitted up the memory into 2-part data memory and instruction memory. This is one that is Harvard architecture. So it is more like a combination of von Neumann and Harvard architecture, in a sense. In the next or next to next model, in the memory, when we start studying memory, you will see we call these guys, this whole thing, as a cache memory. So backward, I'll send all the way to the back. Okay, we call it a cache memory. Your main memory is still sitting outside on the board. Main memory is still sitting outside somewhere. I don't know. Okay, somewhere here, your main memory on the board, and cache memory is in the processor, inside the processor. Main memory. Main memory is the one, like usually if you want to upgrade your RAM into your system, you take out some memory card and punch in the new memory card with a higher capacity. That's the main memory on the board. And the cache memory is a part of the processor which caters to these two distinct memory sections, data memory and instruction memory. So from this angle, processor and the cache memory angle, this is an Harvard architecture. But overall, it uses the main memory. Your main program resides here, data resides here. Only part of them brought into the data cache and brought into the instruction cache. And we'll discuss about this advanced concept in that memory when we start studying the memory systems. All right. But point is this. Like if you look at the system from this whole perspective, the processor, controller, main memory, etc., it is still a von Neumann architecture. But internally, it is somewhat hybrid. It is a hybrid between a Harvard architecture and the von Neumann architecture. Question? Okay, so what else can we do tonight? So you guys have started on the project 3 already, or taking some rest after the project 2?
Please definitely taking some rest.
It's coming up. And each of this lab, as I said, lab 11 till the end of this semester, all this lab will give you the task to complete each week. So please follow through that one. Anyone wants to sum up your project 2 experience?
Hey, Professor, I have a question about Project 3.
Yes, Jerry.
For the ALU, are you looking for a combinational or a sequential ALU?
A combination.
Okay, thank you.
Yeah, let's keep our life simple. It is complicated enough till now. What else? So anyone wants to sum up your project 2 experience? Traumatized or easy peasy?
I do feel like traumatized is a good summary here.
Okay, but did it work at the end?
I mean, the files you gave worked fine, but I mean, yeah, it would have been great if you had just given us a, you know, a .dat file that tests every single instruction. But apart from that, I think it was very complicated.
Yeah, let me take that note. Like I have a plan, long time plan of doing that. Maybe some of you can help me to actually come up with that testing. That would be great.
Yeah, because as far as I know for my project, I mean, I can be only sure about the files you gave us. I tested those, and everything else outside of those, I'm not so sure.
Okay. But at least do you have now a much more clear concept that how a processor executes any program, including Facebook and Google?
Yeah, I would say that, but I've also, lost a lot of other knowledge that I might have had before. No, I'm just joking, Professor.
Right. So basically it is all about, linking different concepts together. They are all part of the same system. Like not only these classes, like your operating system class experience and your compiler system software, that kind of class experience, that course experience, you need to start linking them together. Then only you can actually grasp the bird's eye view of the whole system, how it fits together, how it works in conjunction with each other's concept. Okay, so please try to make this, and that goes in a very, very long run. If you have that clear concept clear, combining the knowledge of those different courses into one single mindset that how my laptop works, that will go in a very, very long run for you in your working life. Any other questions, comments, anything to share?
Can you go over what the task was doing exactly inside of the like you provided it in the PDF of the like how to do the project, but what was it doing inside of the project? Like if I put it in my control unit module, what does it do?
So that is a task you can call to print what instruction being executed at that point. So that task basically parse the instruction codes and formats and try to kind of, you can say that reverse assembly. From the machine code, it tries to print out the corresponding assembly to show what is the current instruction is. So now the usage would be like maybe for debugging your project, you can just call the task maybe at the instruction fetch, or after the instruction fetch is done, maybe during the instruction decode register fetch. If you call the task, you will see at that point what instruction being came up to you.
So you do the calls inside the control unit module?
Yeah.
Okay.
It's for printing, like it's kind of insertion of print statement in your software program and see what is internally going on.
Yeah. I think I was just writing all the time to test everything. like doing the $ right and then just writing certain
That's
things.
another way. Yeah, I wanted to give you the task in the sense to show you how, when you read from the instruction memory, how do you parse it and determine what are the different fields and what are the different instruction is. And from that, it should be easy enough, like saying that, okay, if this is my opcode, this is the action I need to do during the instruction fetch or decode or exe. It's a huge name, like series of if then else or switch case block, whatever way you want to implement the thing in the Verilog. But bottom line is that it's a if then else statement, chain of it.
Okay. I think I noticed some ports in the files that you provided that maybe were kind of declared with the incorrect size.
Yeah, I know that. Yeah, but that's not a problem in the simulation.
Yeah, it just would provide warnings, but I was just and I replaced them with the macros that had the correct size from the definition file, but I was wondering if you wanted to like know specifically which ones.
No, that's
So
fine. That's fine.
okay.
All right, then I don't have anything more to discuss tonight with you. And if you don't have anything for me, then we can stop tonight and then we'll meet in next week with more on this pipeline.